All things are made of atoms. They are everywhere and they constitute everything. Not just the solid things like walls and tables, but the air in between. The basic working arrangement of atoms is the molecule. A molecule is simply two or more atoms working together in a more or less stable arrangement. Add two atoms of hydrogen to one of oxygen, and you have a molecule of water. Atoms, in short, are very abundant. They are also fantastically durable. Because they are so long-lived, atoms really get around. Every atom you possess has almost certainly passed through several stars and been part of millions of organisms on its way to becoming you. We are each so atomically numerous and so vigorously recycled at death that a significant number of our atoms came from the Buddha and Genghis Khan and Beethoven and any historical figure you can name. It takes atoms some decades to become thoroughly redistributed, so sadly we are not yet with Elvis Presley. The abundance and the extreme durability of the atom that makes them so useful, and the tininess that makes them so hard to detect and understand. These realizations came from an English Quaker, John Dalton. Dalton's simple insight was that at the root of all matter are exceedingly tiny, irreducible particles. Neither the idea of atoms nor the term itself was exactly new. Both had been developed by the ancient Greeks. The first real hero of the atomic age was Ernest Rutherford. He was born in 1871 in New Zealand, and in 1895 he won a scholarship to attend the Cavendish Lab at the Cambridge University. In 1910, Rutherford fired ionized helium atoms at a sheet of foil. After considerable reflection, he realized there could be one possible explanation: the particles that bounced backward striking something small and dense at the heart of the atom, while others sailed uninterrupted. He soon realized that the atom was mostly empty space, with a dense nucleus at the center. We now know that neutrons and protons occupy the atom's nucleus. The nucleus of an atom is tiny but fantastically dense. If an atom were expanded to the size of a cathedral, the nucleus would be only about the size of the fly, but a fly many thousand times heavier than the cathedral. It is still a fairly surprising notion to consider that the atoms are mostly empty space. Thus, it is not that surprising when you know that sitting in a chair, you are not actually sitting there, but levitating above it at a height of 1 angstrom. Your electrons and its electrons are implacably opposed to any closer intimacy. The picture that everyone has in mind about the electrons that are flying around the nucleus is fairly false. It's actually more like the blades of a spinning fan, managing to fill every bit of space in their orbits simultaneously. Atomic behavior was then concluded to be unlike ordinary experience, and it's very difficult to get used to it, and it appears peculiar to everyone. All the way to France, Prince Louis Victor de Broglie found that certain anomalies in the behavior of electrons disappeared when one regarded them as waves. This observation excited the attention of the Austrian Erwin Schrödinger, who then made up the wave mechanics. At the same time, the German physicist Werner Heisenberg came up with competing theory called the matrix mechanics. Finally, in 1926, Heisenberg came up with the celebrated compromise, producing a new discipline that came to be later known as quantum mechanics, which states that the electron is a particle that can be described in terms of waves. You can never predict where an electron will be at any given moment. You can only list its probabilities of being there. This, of course, also seemed very confusing to scientists, and they concluded that things on a small scale behave nothing like things on a large scale. Wolfgang Pauli's exclusion principle states that certain pairs of subatomic particles, even when separated by the most considerable distances, can each instantly know what the other is doing. Suddenly, You needed two sets of laws to explain the behavior of the universe: quantum theory for the world of the very small, and relativity for the larger universe beyond. To explain what kept atoms together, other forces were needed. Two were discovered: the strong nuclear force and the weak nuclear force. The strong force binds atoms together. It's what allows protons to bed down together in the nucleus. The weak force, however, engages in more miscellaneous tasks, mostly to do with controlling the rates of certain sorts of radioactive decay. The weak nucleus force is 10 billion times stronger than gravity. But their influence extends to only the tiniest distances. That's why the nuclei of atoms are so compacted and dense, and why elements with big, crowded nuclei tend to be so unstable. The strong force just can't hold on to all the protons. Elsewhere, real progress was being made, effectively demonstrated by exploding